I'm very glad you're here tonight. Our subject this evening is a quiet argument that has been running through physics for a century. What quantum physics is actually telling us about the world. One small favour before we settle in. The Sleepy Scientist has its own ebook now, complete with full narration, and it's waiting at thesleepyscientist.com. It takes the ideas from these videos and gives them the room they deserve to read or to listen, whichever you prefer. There's a QR code on screen for the first 5 minutes and a link in the description. Picking up a copy is the best way there is to support the channel, and it means a great deal every time someone does. While we're still getting comfortable, drop a comment and tell me which corner of the world you're tuning in from. It never stops amazing me how far these little voyages seem to reach. Now, here is the curious thing about tonight's topic. Nobody seriously doubts that quantum physics works. Its predictions have been confirmed to almost absurd precision, and half the technology in your home quietly depends on it. The trouble starts the moment anyone asks what the equations are describing. Whether a particle has definite properties before anyone looks. Whether measurement forces the universe to make up its mind. Whether every possible outcome plays out somewhere, in a branch of reality we never get to visit. We'll wander through the great interpretations, from Copenhagen to many worlds, to pilot waves, and beyond, and sit with the unsettling fact that they all match the experiments while painting utterly different pictures of what exists. So dim the lights, sink a little deeper into wherever you're resting, and let's open with the puzzle underneath it all. How can a theory be this successful while nobody agrees on what it means? Quantum physics occupies a rather unusual position in the history of science. It is one of the most accurate and successful frameworks human beings have ever created, yet there is still no universal agreement about what its mathematics is telling us the world is actually like. That may sound surprising. Normally, when a theory works this well, we imagine that scientists must also understand exactly what it describes. Quantum mechanics complicates that comfortable assumption. Its predictions have been tested with extraordinary precision, often agreeing with experiment to many decimal places. It tells physicists how atoms absorb and emit light, how electrons behave inside materials, how nuclei decay, and how particles interact at scales far smaller than anything the unaided eye could ever hope to see. The theory is not merely successful in distant laboratories. It is quietly woven through ordinary life. Lasers depend on quantum transitions between energy levels. Semiconductor devices rely on the quantum behavior of electrons inside solid materials. Modern computers, mobile phones, solar cells, light-emitting devices, and much of digital technology would not function without principles derived from quantum mechanics. Nuclear physics uses the theory to explain radioactive decay and the processes that power stars. Chemistry depends on quantum rules to describe how electrons arrange themselves around atomic nuclei and how chemical bonds form between atoms. Medical imaging techniques also rely on quantum properties, particularly the behavior of atomic nuclei inside magnetic fields. Precision atomic clocks use carefully controlled quantum transitions to measure time with astonishing reliability. Experimental quantum computers attempt to exploit superposition, interference, and entanglement to process information in ways that ordinary computers cannot easily reproduce. There is no serious dispute that the mathematical machinery works. The disagreement begins when someone asks a deceptively simple question. What is the machinery describing? Quantum mechanics provides a formal structure. It gives physicists mathematical rules for preparing a system, representing its possible states, predicting the probabilities of different measurement outcomes, and calculating how those probabilities change over time. The formalism is shared remarkably widely. Physicists with completely different philosophical views can use the same equations and arrive at the same experimental prediction. An interpretation tries to explain what those equations mean. It asks what exists behind the calculation. It asks whether the wave function is a real physical object or simply a compact description of our knowledge. It asks whether a particle possesses definite properties before a measurement is made. It asks whether measurement causes a genuine physical change, or merely reveals a relationship that was already present in some deeper form. It also asks where probability enters the world. Perhaps quantum outcomes are fundamentally random, with nature itself choosing among several possibilities. Perhaps the apparent randomness comes from hidden information that is inaccessible to us. Perhaps every possible outcome occurs, but in different branches of reality. Perhaps particles always occupy definite positions while an accompanying wave guides their motion. Perhaps superpositions eventually collapse through a real physical process when a system becomes sufficiently large or complex. These are not small differences in wording. They describe profoundly different universes. In one picture, measurement occupies a special role, and possibilities become actual outcomes when a quantum system interacts with an apparatus. In another, the quantum state never collapses at all, and every allowed result remains present within a branching, universal wave function. In pilot wave theory, particles follow definite paths, guided by a non-local quantum wave. In objective collapse theories, the ordinary equations are altered so that large superpositions genuinely and spontaneously reduce to single outcomes. These proposals do not all belong to precisely the same category. Some are interpretations of the usual mathematical formalism. They retain the standard experimental predictions while offering different accounts of what the symbols represent. Some are reformulations that rearrange or extend the conceptual structure without necessarily changing measurable results. Others are modified physical theories that introduce new dynamics and may, at least in principle, produce experimental predictions that differ slightly from ordinary quantum mechanics. That distinction matters. Copenhagen quantum mechanics, Everettian quantum mechanics, pilot wave theory, and objective collapse models are often placed side by side as though they were simply four different stories pasted onto the same equations. The reality is more complicated. They disagree not only over what exists, but sometimes over which laws are fundamental, whether collapse is real, whether hidden variables are present, and whether future experiments could distinguish one account from another. Even the goal of interpretation is disputed. Some physicists believe a successful theory should describe an observer-independent reality. In that view, physics ought to tell us what exists and what happens whether or not anyone is measuring it. Others take a more operational approach. They argue that a physical theory succeeds when it correctly connects experimental preparations with observable results. Asking what happens beyond every possible observation may be meaningful, they suggest, but it may not be something the theory is required to answer. This creates an unusual disagreement about what would count as a solution. Would a satisfying interpretation need to identify the true physical contents of the universe? Would it need to remove the special role of measurement? Must it explain why only one outcome is experienced? Should it recover probability from deeper deterministic laws? Or is the demand for a single underlying picture itself a leftover from classical physics, carried into a domain where it no longer belongs? There is no universally accepted answer. The disagreement should not be exaggerated. Physicists are not arguing over every calculation, every laboratory result, or every working piece of technology. They routinely use quantum mechanics with remarkable agreement. The uncertainty lies deeper, beneath the layer of practical calculation. The mathematics tells them what results to expect. The interpretations attempt to explain why those results appear, what the wave function represents, and what reality is doing when no measurement has yet produced a definite answer. That is the quiet puzzle at the heart of quantum theory. Humanity has learned to use the rules with extraordinary skill. It can build lasers, clocks, computers, scanners, and detectors from them. Yet behind those achievements remains a strangely basic question. What kind of universe would have rules like these? Before quantum physics unsettled the foundations of science, reality appeared to follow a fairly simple set of expectations. An object was assumed to be somewhere. It was moving at a particular speed in a particular direction. It possessed a measurable amount of energy, and these properties remained real whether anyone happened to be looking at the object or not. A stone resting in a field did not need an observer in order to have a location. A planet continued along its orbit while the astronomers beneath it slept. A cannonball travelled through the air along one definite path, even when fog or darkness prevented anyone from seeing it. This picture was shaped most powerfully by the mechanics of Isaac Newton. Newtonian physics described the motion of objects through forces acting over time. Once the mass of an object, its position, its velocity, and the forces affecting it were known, its later motion could, at least in principle, be calculated. A physical state in classical mechanics was intended to provide a complete description of a system at a particular moment. For a single moving object, this meant knowing where it was and how it was moving. For a larger system, it meant specifying the positions and motions of every relevant part. From that information, the laws of physics could carry the system forwards. The same laws could also be used in reverse. If the present state were known perfectly, the earlier state could, in principle, be reconstructed. The universe resembled an immense machine whose parts followed definite rules, each moment growing from the one before it. This did not mean that human beings could actually predict everything. Determinism and predictability are related ideas, but they are not identical. A deterministic system is one in which the present physical state, together with the laws of nature, fixes what happens next. A predictable system is one whose future can realistically be calculated by someone with limited information, limited measuring instruments, and a limited amount of time. The weather provides a familiar distinction. The atmosphere is governed to a very good approximation by classical equations. Air pressure, temperature, humidity, wind, sunlight, and the rotation of Earth all influence how weather systems develop. Yet tiny uncertainties in the starting conditions can grow into large differences over time. This sensitivity is part of what became known as chaos theory. The system may remain deterministic while its long-term behaviour becomes extremely difficult to predict in practice. The difficulty comes from incomplete knowledge, not from the atmosphere having no definite condition, until someone checks the forecast. Classical probability was normally understood in much the same way. When a shuffled card is drawn from a deck, the card is already in a particular position. The observer simply does not know which card occupies that place. When dice roll across a table, their motion depends on their starting position, speed, rotation, shape, contact with the surface, and collisions with the surrounding air. If every detail could somehow be measured with perfect accuracy and calculated without error, classical mechanics would describe a definite result. The probability reflects ignorance of those details. A large collection of gas molecules offers a more complicated version of the same idea. A room may contain an unimaginably large number of molecules moving in different directions and colliding many billions of times each second. Physicists do not track every collision individually. Instead, they use statistical quantities such as pressure and temperature. The molecules are still assumed to possess definite positions and velocities. Statistics provide a practical summary because the underlying details are too numerous to follow, not because those details fail to exist. Several broader assumptions quietly accompanied this classical picture. One was realism, the idea that physical objects possess properties independently of observation. Another was locality. An object was expected to be influenced directly by its immediate surroundings, while effects travelling across a distance required some physical process to carry them. Causality suggested that events occur through understandable chains of influence. Causes precede their effects, and changes do not simply appear without physical explanation. Separability meant that distant systems could be regarded as individually existing things, each with its own physical state. Even when two objects had interacted in the past, they could later be described as separate parts of reality. Observer independence completed the picture. The world did not depend on who was examining it. Different observers might possess different information, but they were assumed to be looking at the same underlying reality. These ideas were not always stated explicitly, because classical physics made them feel almost unavoidable. The wave theories of the 19th century also fitted comfortably into this general framework. A wave was an extended physical disturbance. Water waves moved across the surface of a lake. Sound travelled through vibrations in air. Light was described through the electromagnetic theory of James Clerk Maxwell as changing electric and magnetic fields spreading through space. A wave could be distributed across a region, but it was not normally interpreted as a list of possible outcomes. It represented a real physical condition that evolved continuously. The early discoveries of quantum physics gradually made this familiar picture difficult to maintain. Max Planck found that the exchange of energy between matter and radiation could be described using discrete quantities rather than an unrestricted continuum. Albert Einstein argued that light itself sometimes behaved as though its energy arrived in individual packets. This helped explain the photoelectric effect, in which light striking a material releases electrons only when each packet carries sufficient energy. Niels Bohr introduced discrete energy levels into his model of the atom. Electrons could occupy certain allowed states, while the classical paths between them appeared to be missing from the description. Louis de Broglie proposed that matter possessed wave-like properties, extending the strange dual behavior of light to particles such as electrons. Werner Heisenberg developed a form of quantum mechanics that focused on observable transitions rather than imagined electron orbits. Erwin Schrödinger created a wave equation that successfully described atomic systems, although the meaning of the resulting wave function soon became a source of disagreement. The new mathematics worked, but it no longer described reality in the old familiar manner. A quantum state did not simply resemble a classical list of definite properties. It contained amplitudes connected with several possible outcomes. Measurements seemed to play an unfamiliar role. Certain properties could not be assigned simultaneous precise values in the ordinary classical way. Probability also appeared to be woven into the theory more deeply than ignorance about shuffled cards or rolling dice. Physicists were therefore left with an uncomfortable choice. They could abandon some of the classical assumptions, reinterpret what a physical state was supposed to represent, or search for a deeper theory restoring a more familiar reality beneath the quantum formalism. The interpretations problem emerged because the old expectations had stopped fitting neatly around the new science. Quantum mechanics did not merely provide unusual answers, it changed the kinds of questions that could be asked about a physical system, and challenged the assumption that a successful theory must describe the world as a collection of objects carrying definite properties through space. The argument over meaning began in the space between those two pictures. On one side stood the classical expectation of a reality that was definite, local, separable, and independent of observation. On the other stood a mathematical theory that predicted nature with extraordinary accuracy, while refusing to fit comfortably into any of those categories. Beneath the disagreement about what quantum physics means, there is a remarkably stable mathematical structure that almost every physicist accepts. A researcher who believes in a branching universe can use the same equations as one who believes particles follow definite hidden paths. A physicist who treats the wave function as a real feature of nature can calculate alongside someone who regards it mainly as a tool for organizing expectations. They may disagree profoundly over the picture behind the mathematics, yet still predict the same pattern on a detector screen. This shared structure is the mathematical machine of quantum mechanics. At its center is the quantum state. In many situations, the quantum state is represented by a wave function. The wave function does not simply list one definite position, one definite momentum, or one definite energy. Instead, it contains information about the possible outcomes of measurements and about the relationships between those possibilities. Those relationships are essential. A quantum state is not merely a bag containing several ordinary alternatives, as though nature had secretly chosen one and neglected to inform us. The different possibilities carry mathematical quantities known as amplitudes. These amplitudes can reinforce or cancel one another when alternative processes are combined. That is what produces quantum interference. To understand where quantum states live mathematically, physicists use an abstract structure called Hilbert space. Hilbert space is not another region of the universe hidden behind the stars. It is a mathematical space whose points represent possible quantum states. An ordinary map uses 2 or 3 directions to identify locations. Hilbert space can require far more dimensions because each independent possibility contributes another direction to the mathematical description. For a system with only 2 possible states, Hilbert space can be imagined using a simplified comparison with arrows pointing in different directions. An electron spin, for example, may be described using 2 basic alternatives relative to a chosen measurement direction. More complicated systems require larger spaces. A particle that can occupy many positions needs an enormous collection of possible state components. A system containing several particles becomes more complicated still, because the complete state must describe the possible relationships among all of them. A quantum state is represented by a vector in Hilbert space. The direction of that vector contains the physically relevant information, while its overall mathematical size is adjusted so that the total probability of all possible outcomes equals 1. This language allows quantum states to be added together. The ability to combine states is known as the superposition principle. Suppose a particle has one quantum state associated with being detected in one region, and another associated with being detected somewhere else. Quantum mechanics permits a new state formed from a combination of both. This does not automatically mean that the particle is an ordinary classical object secretly sitting in one location, while we remain uncertain about which location it chose. A superposition can produce interference, revealing that its components maintain a precise mathematical relationship. A classical mixture behaves differently. Imagine a sealed box prepared so that a ball is placed on the left half of the time and on the right half of the time. The ball always has one definite location. The mixture reflects ignorance about which preparation occurred. A quantum superposition of left and right can contain phase relationships that affect later measurements. When the alternatives are recombined, their amplitudes may strengthen one another in some outcomes and cancel in others. No ordinary mixture of hidden left and hidden right positions reproduces that behavior in the same way. Once the initial quantum state is specified, its normal evolution is governed by the wave equation introduced by Erwin Schrödinger. Written in spoken form, the central rule says, the change of the quantum state over time is determined by the total energy operator acting upon that state. The total energy operator is often called the Hamiltonian, named after William Rowan Hamilton. It represents the kinetic energy of a system, its potential energy, and the interactions among its parts. Schrödinger evolution is smooth, continuous, and deterministic. Given the exact state of a closed quantum system and the relevant energy operator, the equation determines how the wave function develops. It does not roll a mathematical die at every instant. The probabilities change according to a precise rule. This creates one of the deepest tensions in quantum theory. The wave function evolves deterministically between measurements, yet individual measurement outcomes appear probabilistic. The mathematical formalism therefore seems to contain two rather different kinds of change: smooth evolution and the selection of a definite observed result. Schrödinger's wave mechanics was not the first complete version of quantum mechanics. Werner Heisenberg had already developed matrix mechanics. Instead of picturing electron waves moving through space, Heisenberg organized measurable quantities into arrays of numbers called matrices. The order in which these matrices are multiplied matters. In ordinary arithmetic, changing the order of two numbers does not change their product. In matrix mechanics, changing the order can produce a different result. This mathematical feature became crucial for quantities such as position and momentum. Erwin Schrödinger's wave mechanics and Werner Heisenberg's matrix mechanics initially appeared very different. One seemed to describe waves. The other worked through abstract tables of observable transitions. Physicists soon discovered that the two approaches were mathematically equivalent. They used different languages to describe the same underlying structure and produce the same experimental predictions. Paul Adrian Maurice Dirac helped place these approaches inside a broader and more elegant framework. His notation made it easier to represent quantum states, transformations, measurements, and probability amplitudes without committing to one particular physical picture. This unification revealed an important lesson. Even the mathematical form used to express quantum mechanics need not determine its interpretation. To connect the wave function with actual experimental frequencies, physicists use the probability rule introduced by Max Born. In spoken form, the rule says, the probability of a particular measurement result is given by the squared size of the quantum amplitude associated with that result. A quantum amplitude can contain positive, negative, or more generally complex mathematical information. It is not itself an ordinary probability. Only after its size is squared does it yield a non-negative quantity that can be interpreted statistically. This distinction allows amplitudes to interfere before probabilities are produced. If two alternatives contribute amplitudes to the same final result, the amplitudes are combined first. Their squared total then determines the probability. Depending on their relative phase, they may reinforce one another, partially cancel, or cancel completely. That is why an interference pattern can contain bright regions where detections are common and dark regions where they are almost absent, even when particles arrive one at a time. Measurements are represented through mathematical objects called operators. An operator describes a physical observable, such as position, momentum, energy, or a component of spin. Each operator has a collection of possible measurement values known as eigenvalues. The corresponding quantum states are called eigenstates. When a system is in an eigenstate of a particular observable, measuring that observable produces the associated value with certainty, at least in the idealized formalism. A general quantum state may be a superposition of several eigenstates. The Born rule then assigns a probability to each possible result. Quantum mechanics does not require every observable to possess one ordinary pre-existing value in every state. In particular, different operators may be incompatible. Position and momentum provide the most famous example. Their operators do not commute, meaning that the order in which their mathematical actions are applied affects the result. This structure leads to Werner Heisenberg's uncertainty relation. Written without symbolic shorthand, the central statement is, the uncertainty in position multiplied by the uncertainty in momentum cannot be smaller than 1/2 of the reduced Planck constant. This is not merely a complaint about clumsy measuring equipment. It reflects the structure of quantum states themselves. A state sharply concentrated in position must be spread across a range of momenta, while a state with narrowly defined momentum must extend across a wider range of positions. The same framework also produces entanglement. When two quantum systems interact, their combined state may become impossible to divide into a separate complete state for each part. The whole then possesses a well-defined quantum state, even though neither component has its own independent pure state. Measurements performed on entangled systems can display correlations stronger than any local hidden variable model can reproduce. For systems entangled with an environment, physicists often use a density matrix rather than an ordinary wave function. A density matrix can describe both pure quantum states and statistical mixtures. It allows physicists to represent situations in which some information is unavailable, or a subsystem has become correlated with degrees of freedom that are not being measured. This becomes especially important when studying decoherence, open quantum systems, thermal behavior, and measurement devices. A statistical mixture and a quantum superposition may sometimes produce similar probabilities for one particular measurement, but they are not generally the same physical or mathematical object. Carefully chosen interference measurements can reveal the difference. These ingredients form the shared machinery: Hilbert space, quantum states, superposition, operators, Schrödinger evolution, the Born probability rule, uncertainty, interference, entanglement, and density matrices. Together, they predict the statistical distributions observed in experiments with astonishing reliability. What they do not automatically provide is one agreed picture of reality. The formalism tells physicists how to calculate what may be observed. It does not plainly announce whether the wave function is a physical field, a catalogue of information, a branching structure, a guide for particles, or something else entirely. The machine produces the correct answers. The argument begins when physicists look inside it and ask what all its moving parts are supposed to be. Once the mathematical structure of quantum mechanics is laid out, one question appears almost immediately. What is the wave function supposed to be? The mathematics treats it as the central description of a quantum system. It evolves according to Erwin Schrödinger's equation, produces interference, becomes entangled with other systems, and supplies the amplitudes used to calculate measurement probabilities. Yet none of this by itself tells us what kind of thing the wave function represents. One possibility is that it corresponds to a real physical condition. In this view, the wave function is not merely a convenient piece of bookkeeping. It describes something that genuinely belongs to the system and exists independently of what any observer happens to know. Philosophers of physics often describe this as an ontic view of the quantum state. The word ontic refers to what physically exists. An ontic wave function might be treated as a real field, a fundamental structure, or a complete state of reality. Different interpretations disagree about its precise nature, but they share the idea that changing the wave function means changing something in the world rather than merely changing someone's information. A contrasting possibility is that the wave function is epistemic. An epistemic state represents knowledge, information, uncertainty, or expectation. A weather forecast does not cause tomorrow's rain. It summarizes what is known about the atmosphere and assigns probabilities to possible outcomes. In a similar way, an epistemic interpretation may treat the wave function as a description of what an observer knows about a quantum system rather than as the system's complete physical reality. This raises the question of completeness. If the wave function is complete, then nothing deeper is required to describe an individual quantum system. The probabilities, superpositions, and uncertainties within the formalism are fundamental features of nature. If it is incomplete, the wave function may resemble a statistical summary hiding additional physical facts. Those facts are often called hidden variables. They might include definite particle positions, undiscovered properties, or some deeper state that determines what the system is really doing. David Bohm's pilot wave theory takes this second route. The wave function remains important, but it is supplemented by particles possessing definite positions. The wave guides their motion, while the complete description contains more than the wave function alone. The idea of a physically real wave function also creates a spatial difficulty. A wave, such as sound, spreads through ordinary three-dimensional space. An electromagnetic wave has values associated with locations in that familiar space. A wave function for one particle can also be written in relation to positions in 3 dimensions. For several particles, however, the complete wave function generally lives in configuration space. A system containing 2 particles requires a mathematical space with 6 position dimensions. 3 describe the possible location of one particle and 3 describe the other. A system containing 100 particles requires 300 position dimensions before other properties are included. The wave function therefore does not resemble an ordinary wave quietly rippling through the room. If it is physically real, physicists must explain how something defined in a high-dimensional configuration space gives rise to the 3-dimensional world of tables, detectors, planets, and people. Another possibility is that a wave function does not describe one individual system at all. According to an ensemble interpretation, it applies only to a large collection of systems prepared in the same way. The probabilities then describe the frequencies expected across repeated experiments. A single electron may possess some deeper definite condition, while the wave function describes what happens when many similarly prepared electrons are examined. This can make quantum probabilities feel more familiar. Yet interference and entanglement place pressure on any simple attempt to treat the wave function as nothing more than ordinary ignorance about hidden classical properties. Some physicists avoid making strong claims about microscopic reality altogether. Instrumentalism treats quantum mechanics primarily as a reliable procedure. A laboratory preparation is represented mathematically, the equations are applied, and probabilities are calculated for possible measurement results. From this perspective, demanding a detailed picture of what happens between preparation and observation may be unnecessary. The theory succeeds by connecting what physicists do with what their instruments record. Instrumentalism has the advantage of caution. It avoids inventing objects or processes that cannot be observed directly. Its critics argue that science should aim for more than an instruction manual, especially when the same formalism is used to describe atoms, stars, detectors, and perhaps the universe itself. The debate has also been sharpened by mathematical results. Matthew Pusey, Jonathan Barrett, and Terry Rudolph developed a theorem examining models in which the wave function represents incomplete information about a deeper physical state. Their results showed that a broad class of models cannot reproduce all quantum predictions if distinct quantum states merely correspond to overlapping distributions of the same underlying realities. The theorem places serious pressure on simple epistemic interpretations. It suggests that differently prepared wave functions must correspond to genuinely different physical situations under the assumptions used in the argument. It does not, however, prove that every imaginable epistemic interpretation is impossible. A central assumption is preparation independence. This means that systems prepared independently are assumed to possess independent underlying physical states. Some proposed models reject or modify that assumption. Others redefine what counts as the underlying state. The theorem therefore narrows the available possibilities rather than ending the debate completely. Every interpretation must eventually confront the same set of questions. Is the wave function real, informational, relational, or purely operational? Does it completely describe an individual system? Why does it evolve according to quantum equations? How does a structure containing several possible outcomes relate to the single definite world people seem to experience? The wave function sits at the center of quantum mechanics, yet its physical identity remains unsettled. Physicists agree remarkably well about how to use it. They remain far less certain about what, if anything it is. The measurement problem begins when quantum mechanics is applied not only to a tiny particle, but also to the instrument attempting to measure it. A microscopic system may begin in a superposition of several possible states. An electron, for example, can be described as having more than one possible spin result relative to a chosen direction. Before measurement, the wave function includes an amplitude for each outcome. According to Erwin Schrödinger's equation, this wave function evolves smoothly and predictably. Its development is deterministic, meaning that the state at one moment fixes how the state changes at the next. Superpositions are not normally destroyed by this evolution. They simply change form while remaining superpositions. Textbook quantum mechanics then introduces a second kind of change. When a measurement occurs, the wave function is said to collapse. Instead of continuing to contain several possible outcomes, it suddenly produces one definite result. Max Born's probability rule determines how likely each result is, but it does not identify in advance which particular result will occur. The difficulty is that the theory does not clearly explain why measurement should obey a different rule from every other physical interaction. Imagine a particle prepared in a superposition of two possible positions. A detector is arranged so that one light appears when the particle is found on the left, and another appears when it is found on the right. If the particle and detector both obey ordinary Schrödinger evolution, they become entangled. The mathematics develops into a combined state containing one component in which the particle is on the left and the detector records left, alongside another component in which the particle is on the right and the detector records right. Nothing in the smooth evolution selects only one of them. The detector does not simply rescue the situation by being larger. According to the quantum equations, it joins the superposition. If the detector is connected to a computer, the computer becomes entangled as well. If a scientist reads the screen, the mathematical chain can extend to the scientist's eyes, nervous system, and recorded memory. John von Neumann described the sequence as the measurement chain. The microscopic system influences the apparatus influences the observer. Each stage becomes correlated with the previous one, yet the formalism does not provide an obvious boundary at which the several possible records become one actual record. This produces the definite outcome problem. Observers do not normally experience several incompatible results at once. A detector points one way, a screen displays one number, a laboratory notebook contains one entry. The complete wave function, however, appears capable of retaining components corresponding to all possible outcomes. The question is not merely why the other outcomes are hidden, it is why one outcome becomes the experienced reality at all. There is also a preferred basis problem. A superposition can be expressed using different mathematical sets of states. The measuring apparatus nevertheless settles into familiar alternatives, such as a pointer indicating one definite position or another. It does not appear in some arbitrary superposition of pointing partly left and partly right. Environmental decoherence helps explain why certain stable states are selected over extremely delicate combinations. Interactions with air molecules, photons, and surrounding matter rapidly suppress visible interference between macroscopic alternatives. Even so, decoherence alone does not select one uniquely experienced result from the complete state. Probability creates another puzzle. Schrödinger evolution is deterministic, while measurement outcomes appear random. If collapse is fundamental, physicists must explain why and when the deterministic evolution gives way to a probabilistic event. If collapse never occurs and every possible outcome remains present, as in Everettian quantum mechanics, probability becomes puzzling in a different way. What does it mean to say that one result is more likely when every result with a non-zero amplitude occurs somewhere in the branching state? Erwin Schrödinger exposed the macroscopic difficulty through his famous cat thought experiment. A cat is placed in a sealed box with a quantum event linked to a mechanism that could release poison. If the quantum event remains in a superposition, the mathematics appears to connect it with a combined state, containing both a living cat and a dead cat. Schrödinger was not suggesting that ordinary cats casually exist in visibly impossible conditions. The thought experiment was designed to show how strange the formalism becomes when microscopic superpositions are extended without explanation into the everyday world. Eugene Wigner later sharpened the difficulty by imagining an observer inside a sealed laboratory. Wigner's friend measures a quantum system and records one definite result. From the friend's perspective, the measurement has already produced an outcome. Wigner, remaining outside and isolated from the laboratory, may still describe the friend apparatus and particle as one uncollapsed quantum superposition. The two descriptions appear to disagree about whether a definite event has occurred. This is not a practical engineering problem caused by imperfect detectors. A more sensitive instrument can improve accuracy, reduce noise, and distinguish outcomes more reliably. It cannot, by itself, explain why the quantum state yields one actual record rather than several entangled possibilities. John Stuart Bell objected strongly to theories that relied on the word measurement without defining it precisely. A fundamental theory, he argued, should not divide the universe vaguely into quantum systems and special measuring devices. It should state exactly which physical processes occur and under what conditions. Three broad responses emerge. One can accept a special measurement rule and treat collapse as part of the standard framework. One can retain only continuous Schrödinger evolution and reinterpret the surviving alternatives. Or one can modify the dynamic so that a real physical collapse occurs naturally when certain conditions are met. Each approach preserves something and sacrifices something else. The measurement problem remains central because it asks where the mathematical possibilities end and the definite world begins. Quantum mechanics predicts the possible results with remarkable precision. What it does not plainly explain is why reality appears to choose one. The Copenhagen Interpretation is often spoken of as though it were one carefully defined answer to the mysteries of quantum mechanics. In reality, it is better understood as a family of related ideas that emerged around the development of quantum theory during the 1920s. Its most influential figures included Niels Bohr, Werner Heisenberg, Max Born, Wolfgang Pauli, and several other physicists working through the consequences of the new mathematics. Many of them were connected intellectually with Bohr's Institute for Theoretical Physics in Copenhagen, which became one of the central meeting places of the early quantum revolution. These physicists broadly agreed that classical ideas could not simply be carried unchanged into the atomic world. They were far less united over precisely what should replace them. Niels Bohr did not describe quantum mechanics in exactly the same way as Werner Heisenberg. Max Born focused heavily on probability, while Wolfgang Pauli sometimes expressed views that were more philosophically adventurous than the careful language used in formal laboratory work. Later textbooks simplified these positions further, often producing a standard account that no single founder would necessarily have endorsed in every detail. The Copenhagen tradition therefore contains several overlapping claims rather than one official doctrine. One of its most important ideas is Niels Bohr's principle of complementarity. Quantum objects can display properties that appear mutually incompatible from a classical perspective. Light and matter may produce wave-like interference in one experimental arrangement, while appearing as individual particles in another. Bohr argued that these descriptions are complementary. Each reveals something necessary about quantum phenomena, but the experimental conditions required to observe one aspect may prevent the simultaneous observation of the other. A double-slit experiment illustrates the point. When no device determines which slit a particle passes through, an interference pattern can emerge. When the experimental arrangement is changed so that path information becomes available, the interference disappears. The particle has not merely been caught behaving badly. The entire experimental arrangement determines which kind of physical statement can be made meaningfully. Bohr also insisted that experiments must be described using classical concepts. The apparatus may ultimately be made from atoms that obey quantum mechanics, yet physicists still need ordinary language such as position, time, detector, path, and recorded result to communicate what was prepared and what was observed. A measurement must leave an unambiguous record. A pointer occupies a readable position. A photographic plate contains a visible mark. A counter registers a definite event. Without this classical language, Bohr argued, there would be no clear way to state what experiment had actually been performed. Werner Heisenberg approached the boundary between quantum systems and measuring instruments somewhat differently. In many accounts, the system is described quantum mechanically, while the apparatus is treated classically. The position of this division can be moved. A detector may initially be treated as part of the classical apparatus, but it can also be included within a larger quantum calculation. This movable boundary became known as the Heisenberg cut. The flexibility is useful in practice. Physicists can place the division wherever it makes the calculation manageable, provided the final predictions remain unchanged. Conceptually, however, the cut creates an awkward question. Is there a real physical boundary separating the quantum world from the classical world, or is the division merely a convenient choice made by the person performing the calculation? The Copenhagen tradition never produced one universally accepted answer. Max Born supplied another central ingredient through his probabilistic interpretation of the wave function. The wave function does not provide a classical trajectory showing exactly where a particle travels at every moment. Instead, it supplies amplitudes from which the probabilities of different measurement results can be calculated. This represented a major departure from classical physics. The absence of a definite trajectory was not necessarily treated as a temporary inconvenience, waiting to be repaired by better instruments. It could be a sign that the demand for such a trajectory had no physical meaning in that experimental situation. From an operational point of view, this approach is extremely effective. A quantum state can be treated as a catalogue of possible outcomes and their probabilities. The experimental arrangement is specified, the quantum equations are applied, and the likely results are calculated. There is no need to imagine a tiny object secretly choosing a path that the theory does not describe. There is also no requirement to treat the wave function as an ordinary material wave spreading through familiar space. Textbook versions of the Copenhagen interpretation commonly add wave function collapse. Before measurement, the quantum state contains several possible outcomes. During measurement, it changes to the state corresponding to the result that was actually recorded. This rule produces the right predictions, but its physical meaning remains uncertain. The theory does not universally specify exactly when collapse happens, how quickly it occurs, how large an apparatus must be, or what physical process separates an ordinary interaction from a measurement. The word measurement performs a great deal of work while remaining surprisingly difficult to define. Copenhagen quantum mechanics is also sometimes described as claiming that human consciousness creates reality. That is too strong and too simple. Some early physicists did speculate about consciousness, knowledge, or the observer in ways that encouraged this interpretation. Yet the more common Copenhagen emphasis was placed on the complete experimental arrangement and the production of an irreversible record. A conscious person does not need to stare continuously at a detector for it to register a result. A photographic plate can retain a mark overnight without patiently awaiting an audience. The strengths of the Copenhagen tradition are closely connected with its restraint. It stays near laboratory practice. It avoids inventing detailed microscopic pictures unsupported by observation. It reminds physicists that every claim about a quantum system is tied to a specific experimental context. Its weaknesses arise in almost the same place. Measurement remains insufficiently defined. The boundary between quantum and classical descriptions is unclear. Collapse works as a rule but lacks an agreed physical mechanism. It is also uncertain whether the wave function describes nature itself, knowledge about nature, or only expectations concerning experiments. These tensions inspired many competing approaches, each attempted in its own way to remove the special status of measurement, classical apparatuses, or observers. The Copenhagen family remains powerful because it tells physicists how to speak carefully about what experiments reveal. It remains controversial because it is much less definite about what reality is doing when no experiment has yet forced the question. Albert Einstein never denied that quantum mechanics was extraordinarily successful. He helped create some of its foundations, and he understood its mathematics as deeply as almost anyone alive. What troubled him was not that the theory failed to predict experiments, it was that its probabilistic description seemed incomplete. Einstein suspected that quantum mechanics might resemble a weather forecast rather than a final account of the atmosphere. A forecast can correctly assign probabilities without listing the exact position and motion of every molecule in the air. In the same way, the quantum wave function might describe what physicists can predict, while leaving out a deeper physical reality beneath those predictions. This was very different from claiming that quantum mechanics was simply wrong. A theory can be accurate within its domain while still failing to describe every underlying detail. Classical thermodynamics correctly describes temperature and pressure without tracking individual atoms. Einstein wondered whether quantum probabilities might eventually be understood through a more complete theory, containing additional physical information. Niels Bohr disagreed with the classical assumptions behind that demand. Their disagreement became especially vivid during the Solvay conferences, where leading physicists gathered to discuss the rapidly developing quantum theory. Einstein repeatedly proposed idealized experiments intended to expose inconsistencies in uncertainty or complementarity. He imagined arrangements involving particles, shutters, clocks, boxes, and carefully timed measurements. Again and again, Bohr examined the complete experimental setup and argued that the uncertainty relations remained intact. These exchanges were not merely intellectual games. They revealed two very different expectations of physics. Einstein believed that physical systems should possess properties independently of measurement. Bohr argued that quantum phenomena could not be separated cleanly from the experimental conditions under which those properties were defined and observed. The disagreement reached its most famous form in 1935. Albert Einstein, Boris Podolsky, and Nathan Rosen published an argument asking whether the quantum mechanical description of physical reality could be considered complete. Their reasoning began with two systems that had interacted and then moved far apart. Quantum mechanics allowed the systems to remain connected through a shared state, even after the distance between them became very large. Later examples often use two particles whose positions, momenta, or spin results are strongly correlated. By measuring one particle, an experimenter can predict with certainty what result would be obtained from a corresponding measurement on the distant particle. Einstein, Podolsky, and Rosen proposed a criterion for identifying an element of physical reality. In simplified form, they argued that if a physical quantity could be predicted with certainty without disturbing the system, then something corresponding to that quantity must already be real. Locality was essential to the argument. If the particles were widely separated, a measurement performed on one should not instantly alter the physical reality of the other. The distant particle therefore appeared to possess the relevant property before the measurement was chosen. The difficulty was that the experimenter could choose which property to predict. One choice of measurement might allow the position of the distant particle to be inferred. Another might allow its momentum to be inferred. Yet standard quantum mechanics did not assign simultaneously definite values to both position and momentum. Einstein, Podolsky, and Rosen concluded that the wave function must be incomplete. It successfully predicted the statistics, but it failed to represent all the elements of reality possessed by the distant system. Bohr responded by challenging the reasoning used to define those elements of reality. He did not claim that a mechanical signal had travelled from one particle to the other. Instead, he argued that the meaning of a physical quantity depended on the entire experimental arrangement. An apparatus designed to establish position creates one physical context. An arrangement designed to establish momentum creates another. These mutually exclusive setups cannot be combined as though they reveal a single classical collection of properties existing independently of every measurement context. For Bohr, the error lay in assuming that the distant particle could be assigned definite properties without considering how those properties became physically definable. The disagreement therefore concerned more than whether information travelled quickly, it concerned separability. Classical separability assumes that a combined system can ultimately be understood through the independently existing states of its individual parts. Once two objects move apart, each should possess its own complete physical condition. Quantum mechanics appeared to resist that division. Erwin Schrödinger recognized the importance of this feature and introduced the term entanglement. He described it not as one peculiar effect among many, but as the characteristic feature that forces quantum mechanics away from classical thought. In an entangled state, the combined system can be precisely described even when its individual parts cannot be assigned separate pure quantum states. The whole possesses information that does not belong independently to either component. Einstein found this deeply unsatisfying. He later referred to the apparent influence across distance as a ghostly action at a distance. The phrase expressed his concern that the theory seemed to undermine local, independently existing reality. Bohr was more willing to accept that quantum systems could not be divided into classical pieces carrying complete, individual properties. At the time, there seemed to be no decisive way to settle the argument. Both sides agreed about the experimental predictions. Their disagreement concerned what those predictions implied about reality, locality, and completeness. For several decades, the dispute remained largely philosophical. Then John Stuart Bell discovered that the assumptions involved were not beyond experimental reach. Bell showed that theories combining locality with certain hidden variables must obey measurable statistical limits. Quantum mechanics predicted that entangled systems could violate those limits. The old disagreement could therefore be carried from conference halls and thought experiments into real laboratories. Einstein had asked whether quantum mechanics concealed a deeper local reality. Bell revealed that nature could be asked directly. John Stuart Bell changed the foundations of quantum physics by showing that some questions about reality could be tested rather than discussed only in philosophical terms. In 1964, Bell published a theorem concerning entangled quantum systems. His result created a way to distinguish the predictions of quantum mechanics from a broad class of theories in which particles carry pre-existing information and all physical influences remain local. A theory of this kind is called a local hidden variable theory. The hidden variables would contain physical information not included in the ordinary quantum wave function. This information could determine the results that measuring instruments eventually display. The word local adds an equally important condition. A choice made at one laboratory cannot immediately alter the physical state or result at another laboratory when the two are separated widely enough that even light has not had time to travel between them. Imagine a source producing pairs of entangled particles and sending them in opposite directions. One particle reaches a detector operated by one experimenter, while the other travels to a distant detector controlled by someone else. Each experimenter can choose between different measurement settings. A local hidden variable account might suggest that the particle pair leaves the source carrying a shared set of instructions. Those instructions determine how each particle will respond to every possible detector setting. Because the particles were prepared together, their results can be strongly correlated. However, Bell discovered that any local instruction-based model must place a limit on the strength and pattern of those correlations. That limit is expressed through a Bell inequality. A Bell inequality does not predict what one individual pair of particles must do. Quantum experiments are probabilistic, and single results can look perfectly ordinary. The inequality concerns statistics gathered across many repeated trials. It compares how often the measurement results agree or disagree when the detectors are arranged in different combinations. Local hidden variable theories cannot produce correlations stronger than a particular boundary. Quantum mechanics predicts that carefully chosen, entangled states can cross that boundary. Bell had transformed an argument about locality and reality into a measurable difference. The original theorem was profound, but turning it into a practical laboratory test required additional work. John Clauser, Michael Horn, Abner Shimony, and Richard Holt developed an experimentally useful version, now known by their four surnames. Their inequality allowed real physicists to test Bell's reasoning using available sources, detectors, and measurement settings. In the early 1970s, Stuart Friedman and John Clauser performed an influential experiment using pairs of photons produced through atomic processes. Their results agreed with quantum mechanics and violated the relevant Bell inequality. Later experiments improved the design. During the early 1980s, Alain Aspect, Jean Dalibard, and Gérard Roget used rapidly changing detector settings. The settings were altered while the photons were already travelling, making it more difficult to imagine that the particles had adjusted their behaviour in advance through an ordinary local process. The measured correlations again agreed with quantum predictions. Many further experiments followed. Researchers tested Bell inequalities using photons travelling through optical fibres and open air, trapped ions held inside carefully controlled laboratories, electrons in solid materials, and superconducting quantum systems. Some experiments separated the detectors by kilometres. Others improved detector efficiency so that a much larger fraction of the particle pairs contributed to the recorded statistics. These refinements mattered because early experiments contained loopholes. The detection loophole arose when only a limited portion of the emitted particles were successfully recorded. The locality loophole concerned whether the choice of one detector setting or the production of one result might somehow influence the distance side through an ordinary signal. By 2015, several research groups had performed experiments designed to close the major detection and locality loopholes simultaneously. No real experiment is completely free from every conceivable assumption, but the evidence against local hidden variable models became exceptionally strong. In 2022, the Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger. Their work established violations of Bell inequalities with entangled photons and helped develop the field of quantum information science. The conclusion from these experiments must be stated carefully. Bell tests show that nature cannot be described by local hidden variable theories, satisfying the assumptions used to derive the inequalities. The combination of local causation and predetermined measurement results cannot reproduce the observed correlations. This does not prove that every particle lacks every definite property before measurement. It also does not eliminate all hidden variable theories. David Bohm's pilot wave theory, for example, contains definite particle positions but is explicitly non-local. It avoids Bell's restriction by abandoning the assumption that distant parts of an entangled system are completely independent in the required classical sense. Bell tests do not prove that the Copenhagen interpretation is correct, nor do they prove Everettian quantum mechanics, relational quantum mechanics, pilot wave theory, or an information-centered interpretation. They remove some possibilities without selecting one final picture. The correlations also cannot ordinarily be used to send a controllable message faster than light. Each observer sees a locally random sequence of results. The meaningful pattern appears only when the records from both laboratories are later brought together and compared through ordinary communication. This is the no signal in principle. Quantum correlations violate classical expectations of locality, yet they do not provide a convenient cosmic telephone for sending tomorrow's lottery numbers into a distant laboratory. Different interpretations explain the same results in different ways. Copenhagen approaches may deny that the particles possess definite values before the measurements are performed. Everettian quantum mechanics keeps the complete entangled wave function and places different outcomes within decohered branches. Pilot wave theory accepts genuine non-local guidance. Relational approaches treat properties as facts established between interacting systems. Information-centered interpretations focus on the constraints placed upon an observer's expectations and experiences. Bell's theorem did not end the interpretations debate. It made the debate sharper. After Bell, physicists could no longer assume that quantum mechanics concealed an entirely ordinary world of local objects carrying complete sets of predetermined instructions. Nature's correlations are more powerful than that classical picture allows. Reality had entered the laboratory, answered one question clearly, and left several larger ones quietly waiting. Bell's theorem reveals that quantum correlations cannot be fitted inside a completely local classical picture. Yet the world around us does not appear remotely quantum in the same obvious way. Tables remain in one place. Measuring devices display stable readings. Dust particles do not visibly spread across a room in several incompatible positions. A cup resting beside a bed does not seem to divide into a collection of alternative cups, simply because no one is watching it closely. The everyday world appears solid, definite, and reliably classical. The physical process that helps explain this appearance is called decoherence. Decoherence does not replace quantum mechanics. It follows from applying quantum mechanics carefully to systems that interact with their surroundings. Its importance comes from recognizing that almost nothing in nature is perfectly isolated. The German physicist Heinz-Dieter Zeh was among the first to emphasize the role of environmental interactions in the emergence of classical behavior. During the second half of the 20th century, he argued that the boundary between microscopic quantum systems and macroscopic classical objects could not simply be assumed. It had to be explained through the way systems become entangled with their environments. Wojciech Zurek later developed these ideas extensively. His work clarified how decoherence suppresses observable interference, how certain stable states become selected, and how information about physical systems spreads into the surrounding world. To understand the basic process, imagine a small object prepared in a superposition of two positions. If the object were perfectly isolated, the two components of the state could retain a precise phase relationship. This relationship would allow them to interfere when the experiment was arranged correctly. Perfect isolation, however, is extremely difficult. Air molecules collide with the object. Photons of visible light scatter from it. Infrared radiation is emitted and absorbed. Vibrations pass through the supporting equipment. The object's internal particles interact with one another. Even the surrounding gravitational and electromagnetic environment can carry information about its condition. Each of these interactions can create entanglement. Suppose one component of the object's state places it on the left, while another places it on the right. A passing photon scatters differently depending on the object's position. After the interaction, the photon becomes correlated with the left and right alternatives. Another photon scatters, then an air molecule collides with the object. Then thermal radiation carries away still more information. The phase relationship that originally belonged only to the object is gradually distributed across an enormous combined system containing the object and its environment. The superposition has not necessarily vanished from the complete quantum description. Instead, its coherence has spread into correlations that are practically inaccessible. To observe interference again, an experimenter would need to control not only the object, but also every photon, molecule, vibration, and internal degree of freedom that had become entangled with it. Their quantum states would have to be reversed with extraordinary precision. For a microscopic system in a carefully shielded laboratory, partial control may be possible. For an ordinary macroscopic object, it is hopelessly unrealistic. A useful mathematical description of this situation is the reduced density matrix. A density matrix can represent the state of a quantum system, including situations involving statistical uncertainty or entanglement. When a system becomes entangled with its environment, the complete density matrix describes both together. Usually physicists are interested only in the smaller system. They therefore ignore or mathematically trace over the environmental degrees of freedom. The result is the reduced density matrix of the system alone. Inside this reduced description, some terms represent ordinary probabilities for the available alternatives. Other terms represent coherence between those alternatives and make interference possible. These coherence terms are often called off-diagonal terms. As environmental information spreads, the off-diagonal terms become extremely small. The reduced density matrix begins to resemble an ordinary statistical mixture rather than a visibly coherent superposition. The system then behaves, for all accessible practical purposes, as though it occupies one classical alternative or another. The basis in which this suppression occurs is not arbitrary. Environmental interactions continually monitor certain physical properties more strongly than others. For a large object, position is often especially important because scattered photons and colliding molecules rapidly record where the object is located. States that remain stable under this environmental monitoring are called pointer states. The name comes from a measuring device with a pointer that settles into one readable position. A pointer directed left or right can leave many durable records in the surrounding environment. A delicate superposition of pointing left and pointing right is far less stable because environmental interactions rapidly distinguish between its components. This process is sometimes called environment-induced selection. The environment does not select one outcome in the sense of causing a unique collapse. It selects a set of stable states that can survive repeated interactions without immediately losing their recognizable structure. Pointer positions, localized objects, and approximately classical trajectories are robust. Strange combinations of macroscopically different arrangements are fragile. The difference in decoherence times between microscopic and macroscopic systems can be enormous. An isolated atom or photon may preserve coherence for long enough to produce clearly measurable interference. Scientists can now maintain carefully prepared superpositions in trapped ions, superconducting circuits, molecules, and other controlled systems for times ranging from tiny fractions of a second to much longer intervals, depending on the apparatus and environment. A macroscopic object exposed to ordinary air and light can decohere vastly faster. For a dust grain in a superposition of noticeably separated positions, collisions with surrounding molecules may destroy accessible interference in an unimaginably short interval. Depending on its size, separation, temperature, and environment, the decoherence time can be far shorter than a trillionth of a second. The exact value varies greatly, but the general lesson is firm. Large warm objects surrounded by matter and radiation lose measurable coherence with extreme speed. This helps explain why classical behavior appears so naturally. Objects follow approximately stable trajectories because localized states are continually reinforced by environmental interaction. Measuring devices preserve durable records because their pointer states become correlated with countless surrounding particles. Information about an object also becomes copied into the environment. Light scattered from a table carries information about its position and shape. Many different observers can intercept different photons and still agree that the same table is present. Wojciech Zurek developed the idea of quantum Darwinism to describe this process. Certain stable states effectively survive because information about them is redundantly recorded throughout the environment. An observer does not need to interact directly with the object. Looking at the light reflected from it is enough. The surrounding world acts as a communication channel, repeatedly broadcasting selected information. This redundancy helps create the appearance of an objective classical reality. Many observers can independently access different fragments of the environment and reach compatible conclusions. Decoherence therefore explains several important features of the familiar world. It explains why interference between macroscopic alternatives becomes effectively invisible. It explains why certain measurement outcomes form stable records. It helps identify the preferred basis in which apparatuses display definite-looking results. It also shows how classical behavior can emerge from quantum interactions, without introducing a sharp boundary between microscopic and macroscopic physics. What decoherence does not do is equally important. It does not by itself produce literal wave function collapse. The complete state of the system and environment still contains all the correlated alternatives. One component contains the object on the left and an environment recording left. Another contains the object on the right and an environment recording right. Because these components no longer interfere in accessible observations, the reduced state resembles a classical mixture. Yet an apparent mixture is not automatically the same as one uniquely realized outcome. The definite outcome problem remains. Why does an observer experience one result rather than a collection of non-interfering alternatives? Why does the detector display this reading rather than merely becoming part of a larger state containing every possible reading? Different interpretations answer differently. Copenhagen approaches may treat decoherence as part of the process that makes measurement effectively irreversible, while still retaining some form of collapse or classical description. Objective collapse theories accept decoherence, but add a genuine physical mechanism that eventually removes all but one alternative. Relational interpretations use decoherence to explain how stable facts arise between interacting systems. Consistent histories approaches use it to identify families of alternative histories that no longer interfere and can therefore be assigned probabilities. Everettian quantum mechanics takes perhaps the most direct approach. It accepts the complete decohered state without deleting any of its components. Each stable component is treated as an effectively independent branch of the universal wave function. The branches do not need to be created by an extra collapse law. They emerge because environmental interactions prevent their different records from interfering in any practical way. Decoherence therefore narrows the mystery without completely removing it. It shows how the noisy, definite-looking classical world can arise from quantum evolution. It explains why macroscopic superpositions become inaccessible, and why measuring devices settle into stable alternatives. But it does not decide whether those alternatives collapse, coexist, become relative, or merely describe different possibilities. The visible superposition disappears. The argument over what remains continues. Probability becomes especially difficult in Everettian quantum mechanics because every outcome with a non-zero quantum amplitude remains somewhere within the universal wave function. Ordinary probability usually concerns uncertainty over which event will occur. A coin will land heads or tails. A card will be drawn from one position in a shuffled deck. Before the result is known, several outcomes appear possible, but only one eventually becomes actual. Everettian quantum mechanics does not work this way. When a quantum measurement takes place, the universal wave function develops into several decohered branches. Each branch contains a different result, a corresponding detector record, and an observer who remembers seeing that result. No fundamental collapse removes the alternatives. If every possible outcome occurs, it becomes unclear what it means to say that one result has a greater probability than another. The question can no longer be understood simply as asking which event will exist after the measurement, because all of them will. It is not enough to say that observers become correlated with every possible result. Quantum mechanics predicts very specific probabilities given by Max Born's rule. In spoken form, the rule says, the probability of an outcome is determined by the squared size of its quantum amplitude. Any Everettian account must explain why observers should expect outcomes according to these squared amplitudes, rather than treating every branch equally. A tempting approach is simply to count worlds. If a measurement produces two branches, perhaps each should receive 1/2 of the probability. If it produces 10, perhaps each should receive 1/10. The problem is that decoherence does not generate a unique collection of sharply separated worlds. Branching is continuous, approximate, and extraordinarily complicated. A single laboratory outcome becomes entangled with air molecules, photons, vibrations, computers, memories, and countless other details. Each interaction may produce further distinctions within the total quantum state. There is no fundamental rule stating exactly how many branches exist. One outcome might appear in a mathematical description containing many finely divided branches, while another appears in fewer broader branches. Changing the way the wave function is grouped could change the count without changing the physics. For this reason, Everettian physicists use branch weight rather than branch number. A branch with a larger quantum amplitude receives greater weight. The relevant quantity is the squared size of that amplitude, matching the Bohr rule. The remaining challenge is to explain why this mathematical weight should behave like probability. David Deutsch and David Wallace developed a decision-theoretic approach to this problem. Their argument considers a rational person making choices before a quantum event causes branching. The person knows that several future successors will exist, each experiencing a different outcome. Suppose the person must choose between experiments connected with rewards or losses. Deutsch and Wallace argue that a rational decision-maker who accepts the Everettian framework should value future branches according to their Bohr rule weights. Branches with greater squared amplitude should influence the decision more heavily than branches with very small weight. The argument is not that low-weight outcomes fail to occur, they still exist. Instead, the claim is that rational behaviour under branching uncertainty should follow the same mathematical structure as ordinary probability. Supporters regard this as an explanation of why an Everettian observer should bet, plan and form expectations using Max Born's rule. Critics question whether the reasoning truly derives probability or builds important features of probability into its assumptions about rational decisions. Wojciech Zurek proposed another approach based on a property called environmental assisted invariance, often shortened to invariance. Invariance concerns symmetries of entangled quantum states. In certain situations, a transformation applied to one part of an entangled system can be undone by acting only upon the other part. Zurek argues that when alternatives possess equal amplitudes and can be exchanged through these symmetries, an observer should assign them equal probabilities. More general states can then be divided into combinations of equally weighted alternatives, allowing the Bohr rule to be recovered. This approach attempts to connect probability with the mathematical symmetry of entanglement, rather than with ignorance about hidden variables. Again, the conclusion remains debated. Some physicists see invariance as revealing why squared amplitudes naturally determine quantum probabilities. Others argue that the method assumes ideas about equal likelihood or statistical interpretation that already contain part of the answer. A third approach uses self-locating uncertainty. Before a measurement, an observer knows that several future versions will arise. During the branching process, there may be a period in which each future observer knows that several counterparts exist, but does not yet know which branch relative result appears in the local record. The uncertainty is not over whether the branches exist. It concerns which observer perspective will be experienced from the first-person point of view. This resembles waking in one of several identical rooms, without knowing which room contains you. Every room exists, yet uncertainty remains about your own location within the larger arrangement. Whether this uncertainty is enough to support genuine probability is still disputed. Critics argue that once every future version exists, there is no fact about which one the earlier observer will become. Each successor is equally continuous with the person before branching. Repeated experiments make the issue more concrete. Imagine performing the same quantum measurement thousands of times. The universal wave function develops branches containing every possible sequence of outcomes. Some branches contain frequencies close to those predicted by the Bohr rule. Others contain highly unusual records, such as one outcome appearing almost every time despite having a small assigned probability. The unusual branches do not disappear. However, their total branch weight becomes extraordinarily small. Nearly all of the high-weight structure contains observers who record long-run frequencies close to standard quantum predictions. Everettian supporters therefore argue that a typical observer, measured by branch weight rather than by branch count, should expect to see Bohr rule statistics. Probability is not a difficulty belonging only to many worlds theory. Copenhagen approaches must explain whether probability reflects fundamental randomness, incomplete knowledge, or limits on meaningful prediction. Objective collapse theories introduce real stochastic events, but must explain why their probabilities follow the Born rule. Pilot wave theory is deterministic, yet it must justify the distribution of unknown particle positions that reproduces quantum statistics. Relational and information-centered interpretations face their own questions about whose probabilities are being described and what those probabilities concern. Everettian quantum mechanics makes the puzzle unusually visible, because nothing possible is removed. Every outcome happens, but not every outcome carries equal weight. The theory can reproduce the familiar mathematics of probability. The deeper question is whether branch weight genuinely explains why an observer should expect one experience more strongly than another. One way to avoid this crowded problem is to imagine that only one physical configuration ever occurs. The wave function may still evolve and guide what happens, but reality follows one definite path through the possibilities rather than realizing them all. Pilot wave theory offers a very different answer to the measurement problem. Instead of allowing every possible outcome to remain physically realized, it proposes that particles always possess definite positions. The wave function still exists and still evolves according to quantum mechanics, but only one actual arrangement of particles occurs. The first version of this idea was developed by Louis de Broglie during the 1920s. He imagined particles being guided by an accompanying wave, much as a small object might be directed by a larger pattern moving around it. Louis de Broglie presented the proposal at the Solvay Conference of 1927, but it attracted relatively little support. The emerging Copenhagen tradition appeared more fashionable, and serious technical objections were raised against hidden variable approaches. The theory returned in a much more complete form in 1952 through the work of David Bohm. David Bohm showed that it was possible to construct a precise hidden variable theory, reproducing the ordinary predictions of non-relativistic quantum mechanics. His formulation is now commonly known as de Broglie-Bohm theory, Bohmian mechanics, or pilot wave theory. Its physical picture contains two main ingredients. There is a wave function, which evolves continuously according to Erwin Schrödinger's equation. There are also particles, and every particle possesses one definite position at every moment. The wave function does not merely describe ignorance about those positions, it plays an active role by guiding how the particles move. The guiding relation connects the motion of each particle with the structure of the complete wave function. The exact mathematical expression need not concern us here, but its central meaning can be stated plainly. The velocity of each particle is determined by the quantum wave function and by the positions of all the particles in the system. Once the initial wave function and the initial particle configuration are specified, the later motion is fixed. The theory is therefore deterministic. This produces a particularly clear account of the double-slit experiment. In ordinary quantum language, a particle is prepared in a state that passes through both available slits and later produces interference. In pilot wave theory, the particle itself travels through one slit. It always has one definite position and follows one continuous path. The guiding wave, however, passes through both slits. The two parts of the wave spread out, overlap, and interfere. Their combined structure guides the particle towards some regions of the detector while steering it away from others. Each arriving particle leaves one definite mark. Repeating the experiment many times creates the familiar interference pattern. The particle does not need to divide into two little copies, nor does it need to know, in any thoughtful sense, that another slit is open. Its path is determined by the complete guiding wave, which responds to the entire experimental arrangement. Measurement works in much the same way. Suppose a quantum state contains several possible detector outcomes. During the interaction, the wave function develops separate components corresponding to those results. The measuring apparatus, however, always has one actual particle configuration. Its pointer occupies one definite position. Its screen displays one definite record. The particles inside the observer's brain and notebook also occupy one actual arrangement. A measurement therefore produces a single experienced outcome without requiring fundamental wave function collapse. The complete wave function may still contain other non-overlapping components. These are sometimes called empty wave packets because they contain no actual particle configuration. They continue to exist mathematically and may keep evolving, but the real configuration of the apparatus and observer lies inside only one effective branch. Once those branches have become sufficiently separated through decoherence, the empty components generally stop influencing the actual configuration in any observable way. The theory reproduces quantum probabilities through a condition called quantum equilibrium. If the initial positions of particles across an ensemble are distributed according to Max Born's probability rule, then the guiding dynamics preserves that distribution over time. In spoken form, the rule is, the probability density for particle positions is given by the squared size of the wave function. An observer does not know the exact initial configuration. That missing information makes individual results unpredictable, even though the underlying motion is deterministic. The situation resembles classical statistical mechanics in one respect. A gas may follow definite microscopic dynamics, while its exact molecular state remains unknown. The resemblance is not complete, however, because pilot wave motion is profoundly non-classical. For entangled systems, the velocity of one particle can depend on the positions of distant particles and on the complete shared wave function. The theory is explicitly non-local. This is not an accidental inconvenience that can be quietly removed. Bell's theorem shows that any hidden variable theory reproducing all quantum correlations cannot preserve locality in the classical sense. Pilot wave theory survives Bell's theorem precisely because it does not attempt to be local. A change in the experimental arrangement affecting one part of an entangled system can alter the guiding conditions relevant to a distant particle, even when the separation is enormous. That sounds dangerously close to faster-than-light communication, but an important distinction remains. The distant influence cannot ordinarily be controlled to send a usable message. Under quantum equilibrium, each local observer still sees a random sequence of outcomes. The non-local pattern becomes visible only when the records from both locations are later compared. Pilot wave theory therefore contains non-local dependence without providing a convenient method of transmitting information faster than light. Its strengths are unusually concrete. The ontology is clear. Particles exist. They occupy definite positions. They follow continuous trajectories. Measuring devices are physical systems rather than privileged objects standing outside the theory. There is no fundamental observer, no special role for consciousness, and no vaguely defined moment when possibilities suddenly become reality. The theory also has significant challenges. The wave function for several particles lives in a high-dimensional configuration space rather than ordinary three-dimensional space. Explaining the physical status of such a guiding structure remains difficult. Particle position also appears to receive a privileged role. Other properties, such as spin, are not necessarily additional hidden objects carried independently by the particle. They are represented through the wave function and revealed contextually through interactions. Extensions to quantum fields, particle creation, antimatter, and relativistic physics are possible, but they are less simple than the original non-relativistic model. Building a fully satisfactory version compatible with the structure of space-time remains an active foundational challenge. Physicists also debate why the universe should begin in quantum equilibrium and whether the Born distribution should be treated as a fundamental law, a typical condition, or something emerging dynamically. John Stuart Bell regarded David Bohm's theory as extremely important. It demonstrated that claims declaring hidden variables impossible had been stated too broadly. What experiments ruled out was not every deeper reality, but local hidden variable theories obeying particular assumptions. Pilot wave theory restores definite particles and one actual history. The price is a guiding wave that connects distant parts of reality in a way no classical picture could comfortably contain. Objective collapse theories take a more direct approach to the measurement problem. Instead of interpreting wave function collapse as a change in knowledge, denying that collapse occurs, or adding hidden particle positions beneath the wave function, they alter the equations of quantum mechanics themselves. Collapse becomes a real physical process. It does not wait for a conscious observer. It does not depend on whether a laboratory technician checks a screen. It occurs spontaneously according to additional laws built into nature. The best-known early model was proposed in 1986 by Giancarlo Ghirardi, Alberto Rimini, and Tullio Weber. Their theory begins with the ordinary quantum wave function, which normally spreads and evolves according to Erwin Schrödinger's equation. It then adds rare, random localization events. Each microscopic constituent has a very small probability of undergoing one of these spontaneous collapses. When a collapse occurs, the wave function becomes sharply concentrated around one region of space, rather than remaining spread across several widely separated possibilities. For an isolated microscopic particle, such events are extraordinarily rare. In the original model, the proposed collapse rate was roughly one event for each particle every 100 million years. An electron or atom can therefore remain in a superposition for long enough to display interference in a carefully controlled experiment. A macroscopic object is different because it contains an enormous number of particles. A speck of ordinary matter may contain billions upon billions of microscopic constituents. A measuring device contains vastly more. Although the chance of collapse is tiny for any one particle, the chance that some particle within the complete object collapses becomes much larger. This is the amplification mechanism. When one constituent of a macroscopic object localizes, its entanglement with the other constituents pulls the wider object into the corresponding position. A pointer that is mathematically spread between left and right cannot remain that way for long. One spontaneous localization selects one of the alternatives, and the entire correlated apparatus follows. The theory is designed to preserve quantum behavior at small scales while suppressing it at large scales. Electrons, atoms, and small molecules can remain coherent. Their wave functions may travel along several paths and later interfere. A table, detector, or laboratory instrument contains so many particles that a large spatial superposition collapses extremely quickly. The classical world emerges because macroscopic alternatives are dynamically unstable, rather than merely difficult to observe. This differs from decoherence. Decoherence causes the components of a superposition to lose observable interference as they become entangled with the environment, yet the complete wave function still contains all of those components. Objective collapse goes further. It physically reduces the state so that only one macroscopic alternative remains. Producing a real collapse requires changing the ordinary quantum dynamics. Standard Schrödinger evolution is linear. If two states are individually allowed, their superposition also evolves as the corresponding superposition of their later states. A genuine collapse mechanism must break this simple linear structure. Otherwise, every alternative continues to survive in the complete wave function. Objective collapse theories therefore introduce nonlinear and stochastic behavior. Stochastic means genuinely random. The time and location of a collapse cannot be predicted with certainty, although the theory provides probabilities for where and when it will occur. Philip Pearl developed another important version known as continuous spontaneous localization. Instead of rare, sudden jumps, this approach describes the wave function as being continuously influenced by a random noise field. The state gradually narrows around one position, with the effect becoming stronger for systems containing more matter. The result is similar in spirit. Microscopic quantum behavior remains almost untouched, while large superpositions are rapidly reduced. Other proposals connect collapse with gravity. Laios Diossi suggested that gravitational effects might contribute to the instability of spatial superpositions. Roger Penrose developed a related argument based on the tension between quantum superposition and general relativity. A massive object in two different positions would correspond to two different distributions of matter. In general relativity, those distributions would produce two different space-time geometries. Penrose proposed that a sufficiently large difference between the geometries might be unstable. The superposition would survive only for a limited time before collapsing into one arrangement. In spoken form, the central idea is the lifetime of a gravitational superposition becomes shorter as the gravitational difference between its alternative mass distributions becomes larger. This proposal is physically suggestive, but a complete universally accepted theory connecting gravitational collapse with quantum mechanics has not yet been established. Unlike interpretations that preserve ordinary quantum predictions exactly, objective collapse models can be tested. The added dynamics may produce small side effects. Repeated localization can slightly increase the energy of a system. It may cause anomalous heating, spontaneous radiation, or a gradual loss of interference beyond what ordinary environmental decoherence predicts. Experiments search for these effects in several ways. Matter wave interferometers send increasingly massive particles and molecules along coherent alternatives, testing whether interference survives at scales where collapse might begin to act. Optomechanical experiments attempt to place tiny mirrors, membranes, or suspended particles into quantum states of motion. Cold atom systems allow researchers to control large collections of atoms with exceptional precision. Other experiments search for unexplained radiation from charged particles. Underground detectors reduce cosmic rays and background noise while looking for faint signals that could be produced by spontaneous localization. Precision temperature measurements can also test whether collapse noise causes matter to warm slightly without an ordinary source of energy. So far, no experiment has confirmed that objective collapse occurs. Results have excluded important regions of the possible parameter space. They place limits on how frequent collapses could be, how sharply they localize a wave function, and how strongly any proposed noise field may interact with matter. Those limits do not rule out every conceivable model. Collapse theories contain adjustable constants. A particular experiment may exclude one combination of collapse rate and localization distance, while leaving weaker or differently structured models untouched. This makes the search gradual rather than decisive. The greatest strength of objective collapse is its clarity. One outcome occurs because the laws of physics select one. Measurement requires no special observer, no classical boundary, and no branching collection of equally real results. The same physical process applies to particles, detectors, animals, and planets. The cost is that new physics must be added. The theories introduce extra constants, fundamental randomness, and small departures from energy conservation. Their compatibility with special relativity and quantum field theory is technically difficult. The physical origin of the collapse noise remains uncertain. Most importantly, ordinary quantum mechanics has not yet been observed to fail. Objective collapse therefore offers more than a new story placed over familiar equations. It makes a genuine scientific gamble. Copenhagen approaches accept a special measurement rule. Everettian quantum mechanics removes collapse and keeps every outcome. Pilot wave theory adds definite particle positions while retaining continuous wave function evolution. Objective collapse theories claim that the familiar equations are only approximately correct. Somewhere between a single atom and the enormous objects of everyday life, nature may stop preserving every possibility and quietly choose one. Quantum mechanics is often introduced through individual measurements. A particle is prepared. An apparatus interacts with it. A result appears. This picture is useful, but it places enormous attention on one moment when a measurement seems to occur. The consistent histories approach takes a wider view. Instead of asking only what value appears at one instant, it asks which complete sequences of events can be described consistently across time. The framework was developed through the work of Robert Griffiths, Roland Omnes, Murray Gell-Mann, and James Hartle. Its central object is not merely a state at one moment, but a quantum history. A history is a sequence of physical alternatives extending through several times. A particle might occupy one region at an early moment, another region later, and eventually trigger a particular detector. A measuring device might begin in a ready state, move into one of several possible pointer positions, and leave a lasting record. Each complete sequence forms a possible narrative about how the system developed. In classical physics, one can usually imagine that exactly one detailed history occurs. A planet follows one orbit. A ball travels along one path. Even when the path is unknown, it is assumed to exist independently of anyone's description. Quantum histories are more delicate because alternative sequences can interfere. Suppose a particle can travel from a source to a detector along two different paths. One possible history contains the first route, another contains the second. If the alternatives remain coherent, the corresponding quantum amplitudes may reinforce or cancel one another. In that situation, ordinary probabilities cannot always be assigned separately to the two histories. It may be impossible to say that the particle followed the first path with one probability and the second path with another, while still preserving the correct interference pattern. The alternatives are not behaving like two exclusive classical possibilities. The consistent histories framework therefore asks whether a chosen set of histories is decohered. A family of histories is consistent when interference between its alternatives becomes negligible in the precise mathematical sense required by the theory. Once that condition is satisfied, ordinary probabilities can be assigned to the histories without producing contradictions with the probability rules. In spoken form, the central principle is, probabilities may be assigned to alternative quantum histories only when interference between those histories has been sufficiently removed. Environmental decoherence often helps produce this condition. When a particle interacts with a detector, surrounding photons, air molecules, thermal radiation, and many internal components become correlated with the result. Alternative detector records rapidly lose their ability to interfere. One history may contain a detector pointing left. Another contains the detector pointing right. Once the environment has recorded those alternatives in countless inaccessible details, the histories can be treated as distinct possibilities with ordinary probabilities. The approach does not require a conscious observer to create the result. The particle, detector, laboratory, notebook, and scientist can all be included inside the same physical description. Each is treated as part of one closed quantum system. This is particularly useful because it removes the need for an unexplained boundary separating a quantum object from a classical apparatus. A measurement becomes one kind of physical history among many. It is a sequence in which information about a microscopic system becomes correlated with a stable macroscopic record. No external observer has to stand beyond the equations and announce that a measurement has taken place. However, the framework introduces an important restriction called the single framework rule. A quantum system can often be described using several different consistent families of histories. One family may organize the alternatives according to particle positions. Another may organize them according to momentum. A third may describe different spin values. Each family can be internally meaningful and mathematically consistent. The problem arises when statements from incompatible families are combined as though they belong to one single classical description. The single framework rule forbids this. A statement meaningful within one consistent family cannot automatically be joined with a statement from another incompatible family. Doing so can create apparent contradictions that come not from nature, but from mixing descriptions that quantum mechanics does not permit to be used together. This resembles Niels Bohr's complementarity in one important respect. Different experimental arrangements may support different descriptions, while no single classical picture contains every possible property at once. The consistent histories approach expresses this restriction mathematically, rather than relying only on broad philosophical language. It can describe a quantum system without introducing fundamental wave function collapse. The universal quantum state may continue to evolve, according to Erwin Schrödinger's equation. Histories become probabilistic alternatives when their interference is sufficiently suppressed. Yet consistent histories does not necessarily claim that every alternative forms a physically real world in the Everettian sense. A family contains possible histories to which probabilities are assigned. The framework does not require all of them to be regarded as equally concrete branching universes. This gives the interpretation a position somewhere between traditional collapse accounts and many worlds theory. It retains probabilistic alternatives without requiring an observer-triggered collapse, but it remains cautious about declaring every mathematical possibility to be a separate realized world. Robert Griffiths has emphasized that quantum reasoning must remain inside one consistent framework at a time. Roland Omness developed the logical and mathematical foundations of the approach. Murray Gell-Mann and James Hartle extended related ideas into the study of decoherent histories and quantum cosmology. Quantum cosmology is a natural setting for this framework. The universe as a whole cannot be measured by an apparatus outside it. There is no external laboratory surrounding all of space-time. A theory of the quantum universe must therefore describe observers, measuring devices, galaxies, radiation, and the early cosmos as parts of one closed system. Histories allow physicists to discuss alternative cosmic evolutions without demanding a special observer beyond the universe. One history might contain particular early density fluctuations that later develop into galaxies. Another might contain slightly different fluctuations and a different distribution of a large-scale structure. When interference between broad alternatives becomes negligible, probabilities can be assigned to different cosmic histories. Within the enormous space of possible histories, a quasi-classical domain may emerge. A quasi-classical domain is a collection of approximately stable histories in which large-scale variables follow familiar effective laws. Planets move along recognizable paths. Fluids possess temperatures and pressures. Measuring instruments preserve records. Biological organisms occupy sufficiently stable physical states to remember events and compare observations. These histories are not perfectly classical. They emerge from quantum mechanics through coarse descriptions, environmental interactions, and decoherence. The word coarse is important. A classical-looking history does not track the exact quantum state of every photon and molecule. It groups countless microscopic details into large-scale variables such as position, density, temperature, and momentum. These broad quantities can remain stable enough to form the continuous world of ordinary experience. The framework's most difficult question concerns the existence of several incompatible, consistent families. If more than one family can describe the same system, is one of them physically correct? Supporters argue that the demand for one all-encompassing framework is a classical habit that quantum mechanics teaches us to abandon. Reality may permit several valid descriptions, provided they are not mixed carelessly. Critics worry that this leaves too much freedom. If many incompatible families are equally legitimate, the theory may not explain why one particular account corresponds to the events people actually experience. The framework, therefore, relocates the interpretive problem rather than making it disappear. Instead of asking exactly when the wave function collapses, it asks which families of histories may receive probabilities. Instead of demanding one instantaneous measurement outcome, it studies whole chains of stable correlations across time. Decoherence does much of the physical work by suppressing interference between alternative narratives. What remains unsettled is whether one history becomes uniquely real, whether reality is meaningful only inside a chosen framework, or whether the framework simply provides several compatible ways of organizing quantum possibilities. Consistent Histories offers a quantum world told through complete narratives rather than isolated measurements. The stories become meaningful when they no longer interfere. The mystery is whether nature chooses one story, contains many, or permits only certain ways of speaking about them. Relational quantum mechanics begins with the possibility that physicists have been asking quantum theory to provide something nature does not possess. The usual expectation is that every physical system has one complete state, describing what it is doing from an absolute, observer-independent point of view. A particle should possess one true condition. A measurement should produce one result that becomes equally real for everything in the universe at the same moment. Carlo Rovelli questioned this expectation when he presented the modern relational interpretation during the 1990s. In this view, a quantum state is not an absolute property carried by an object in isolation. It describes the physical relationship between one system and another. The inspiration comes partly from relativity. In classical physics, velocity was often treated as though it belonged directly to an object. Yet velocity is always relative to something else. A passenger sitting inside a moving train is stationary relative to the carriage, but moving relative to the ground. Neither description is mistaken. There is no additional absolute velocity hidden behind them. Albert Einstein's special theory of relativity extended this relational thinking. Observers moving differently can disagree about the time between events, the length of an object, and whether distant events occur simultaneously. Their descriptions are not arbitrary, because precise transformation rules connect them. Carlo Rovelli suggested that quantum states may be relative in a comparable, though not identical, sense. A quantum property becomes definite through an interaction between physical systems. An electron does not necessarily carry one absolute spin value, waiting to be uncovered from every possible perspective. When it interacts with a measuring apparatus, a definite result may become real relative to that apparatus. The result is a physical fact, but it is a relational fact. This does not mean that reality depends upon human opinion. The apparatus cannot simply choose whichever result seems most agreeable. The interaction follows the laws of quantum mechanics and produces correlations governed by Max Born's probability rule. The word observer can easily cause confusion here. In relational quantum mechanics, an observer does not have to be conscious. It need not possess eyes, memories, curiosity, or a laboratory coat. Any physical system capable of interacting with another can serve as an observer relative to that interaction. An atom may observe another atom in this limited physical sense. A photon may interact with an electron. A detector may become correlated with a particle. The important feature is not awareness, but the establishment of a physical relation. Suppose an electron is prepared in a superposition of two possible spin results. It then interacts with a measuring apparatus. Relative to the apparatus, one definite result occurs. The pointer records one value, and the electron possesses the corresponding spin property within that relationship. A second system outside the laboratory may not yet have interacted with either the electron or the apparatus. From its perspective, the combined laboratory can still be represented by a superposed quantum state, containing several correlated possibilities. The electron, therefore, has a definite result relative to the apparatus, while remaining part of a superposition relative to the outside system. At first, this may sound contradictory. How can the same event be definite and indefinite? Relational quantum mechanics answers that the two descriptions concern different physical relations. The mistake is assuming that there must be one absolute quantum state from which every possible observer can read the same complete set of properties. The situation resembles asking whether a passenger is moving or stationary without saying relative to what. Both answers may be correct once the relevant reference system is identified. Relational quantum mechanics therefore rejects the idea of a universal viewpoint hovering above the entire universe. There is no imagined observation point from which every object possesses one complete and absolute quantum state. States are assigned relative to physical systems, and facts arise through interactions. Measurement consequently loses its mysterious status. A measuring device does not stand outside quantum theory. It is an ordinary physical system interacting with another system. When a particle reaches a detector, the interaction creates a correlation. A particular detector record becomes definite relative to the detector. When a scientist later examines the apparatus, another interaction occurs, establishing a corresponding fact relative to the scientist. There is no universal moment of collapse that must become visible simultaneously from every perspective. The wave function may change relative to one system because that system has acquired new information through physical interaction. Another system that has not interacted with the result may continue assigning a different quantum state. This resembles wave function collapse in practice, but the change is relational rather than a single physical contraction spreading across the universe. Environmental decoherence helps explain why the world still appears broadly shared. A measuring device does not interact with only one microscopic particle. Its result becomes correlated with photons, air molecules, nearby equipment, electronic records, and countless internal degrees of freedom. Information about the result spreads into the surrounding environment. As the same record becomes redundantly encoded across many systems, it grows extremely stable. Different observers later interact with fragments of that environment and usually obtain compatible information. One scientist reads the detector, another examines the computer record, a third sees light reflected from the pointer. Each establishes a relation through a different physical interaction, yet all encounter the same durable macroscopic result. The appearance of one common objective world may therefore emerge from a dense network of stable, relational facts. This raises an important challenge. If facts are always relative, why do observers agree so reliably when they compare their records? Relational quantum mechanics must provide consistency conditions, explaining how one observer's result relates to the later experiences of another. The observers should not be able to meet after an experiment and discover completely incompatible records without any physical explanation. Supporters argue that quantum correlations already enforce the required consistency. When two observers interact and compare results, their records become correlated through another ordinary quantum event. Critics remain concerned that the interpretation sometimes speaks more clearly about separate perspectives than about how those perspectives fit into one coherent reality. The difficulty becomes especially vivid in Eugene Wigner's friend thought experiment. Inside a sealed laboratory, Wigner's friend measures a quantum particle and observes one definite outcome. Relative to the friend, a fact has occurred. Eugene Wigner remains outside and does not interact with the laboratory. He may describe the friend, detector, and particle as one larger superposition. Traditional interpretations may treat these accounts as an uncomfortable disagreement over when collapse occurred. Relational quantum mechanics treats them as evidence that quantum states were never absolute. The friend's definite result is real relative to the friend. The superposed laboratory is the appropriate state relative to Wigner before he interacts with it. When Wigner opens the laboratory and communicates with the friend, new relational facts are established. Neither description must be promoted into a universal view, valid independently of every physical relationship. The interpretation offers an elegant removal of the privileged observer and the mysterious quantum classical boundary. It treats measurement as interaction and facts as relations between systems. Its deepest question is whether relational facts form a complete account of reality. Perhaps objects are nothing more than the network of ways they affect other objects. Perhaps demanding absolute properties is no more sensible than demanding an object's absolute velocity. Or perhaps a deeper observer-independent structure is still needed to explain why the relational descriptions fit together as consistently as they do. Relational quantum mechanics replaces one universal state with a web of physical perspectives. Reality does not disappear. It becomes something systems establish with one another. Quantum Bayesianism begins by shifting tension away from the idea that the wave function must describe one objective physical state belonging to the world. Instead, the wave function is treated as an expression of an individual agent's expectations. This approach was developed principally through the work of Christopher Fuchs, Rudiger Schack, Carlton Caves, and David Mermin. It combines the mathematical structure of quantum mechanics with a particular understanding of probability drawn from Bayesian reasoning. In ordinary Bayesian probability, a probability represents a degree of belief. It does not necessarily describe a physical tendency hidden inside an object. It expresses how strongly an agent expects a particular event to occur, given the information currently available. Suppose someone assigns a high probability to rain tomorrow. That probability reflects what the person knows about the weather, the reliability of the forecast, and the evidence already gathered. Another person with different information may assign a different probability without either of them claiming that the atmosphere possesses one small object labelled 70%. Quantum Bayesianism applies this personal understanding of probability to quantum theory. A quantum state describes the expectations held by a particular agent concerning the possible consequences of actions performed upon the external world. Preparing a particle, adjusting a detector, choosing a measurement direction, and recording a result are treated as actions and experiences involving the agent and the world. The wave function is therefore not a physical substance moving through space. It is not an objective field shared identically by every observer. It is a compact mathematical expression of the probabilities one agent assigns to possible future experiences. Another agent may possess different information, and therefore assign a different quantum state to the same physical system. This does not mean that every opinion is equally valid. Quantum probability assignments must obey strict mathematical relationships. An agent cannot choose probabilities carelessly and still expect to make consistent decisions. The most important constraint is Max Born's probability rule. In many interpretations, the Born rule is treated as a law connecting an objective wave function with the frequencies of physical outcomes. Quantum Bayesianism gives it a different role. It treats the Born rule as a normative rule. A normative rule states how a rational agent ought to organize different beliefs so that they fit together coherently. In spoken form, the central idea is the Born rule connects the probabilities an agent assigns to different possible actions and experiences. The rule does not physically force one outcome to appear. It does not describe a mechanism pushing a wave function into a smaller shape. Instead, it tells the agent how different probability judgments must be related when quantum systems are involved. This interpretation changes the meaning of wave function collapse. Suppose an agent assigns probabilities to several possible measurement outcomes. The experiment is performed, and one result is experienced. The agent now possesses new information. The quantum state changes because the agent's expectations must be updated in light of that experience. Collapse resembles the updating of a probability distribution after new evidence arrives. Nothing has to travel instantly through space. No physical wave needs to vanish from distant regions of the universe. What changes is the agent's catalogue of expectations. This may sound as though the external world has been reduced to personal belief, but advocates of quantum Bayesianism reject that conclusion. The world is real. It resists the agent, responds to actions, and produces experiences that the agent cannot simply choose in advance. Quantum probabilities are personal, but the experiences that prompt those probabilities are encounters with something external. Christopher Fuchs has emphasized that the world is not a passive stage merely revealing facts already written into it. A measurement is an active intervention, and the outcome is a genuinely new event arising from the interaction between the agent and the world. The result is not simply uncovered like a card that was already lying face down on a table. In this view, nature contains genuine novelty. Quantum Bayesianism also offers a distinctive response to entanglement, an apparent non-locality. Imagine two entangled particles sent to distant laboratories. An agent measures one particle and obtains a result. The quantum state assigned to the distant particle may then change immediately. If the wave function were an objective physical object, this sudden change could appear to involve something travelling across the distance. Quantum Bayesianism interprets the change differently. The agent has received new information. The probabilities assigned to possible future experiences involving the distant particle must therefore be updated. A change in belief is not a physical signal. The agent cannot use the update to control the results seen at the distant laboratory. The local outcomes remain individually unpredictable, and meaningful correlations emerge only when records are later compared through ordinary communication. The apparent instantaneous change therefore occurs in the agent's expectations rather than through a controllable influence passing between the particles. At first glance, quantum Bayesianism can resemble instrumentalism. Both approaches resist treating the wave function as a straightforward picture of microscopic reality. Both focus heavily on preparations, actions, outcomes, and predictions. The difference is that quantum Bayesianism attempts to say something positive about the character of the world. It does not merely advise physicists to calculate and remain silent. It proposes that probability is personal, that measurement outcomes are experiences, that agents participate actively in physical events, and that the external world is capable of producing genuinely new responses. The interpretation, therefore, contains a philosophical picture, even though it avoids presenting the wave function as an objective object. Its critics argue that this picture places too much emphasis on the agent. A fundamental physical theory is normally expected to describe what exists independently of anyone's beliefs. Stars formed long before human observers appeared. Atoms interacted before laboratories were built. The early universe developed without anyone assigning probabilities to it. Critics therefore ask what quantum Bayesianism says the world itself is doing. If the wave function belongs only to an agent, what objective physical structure explains why the Bohr rule has its precise mathematical form? Why do different agents using quantum mechanics reach compatible expectations? What is the world made of when no agent is interacting with the system? There is also disagreement over what qualifies as an agent. Must an agent be conscious? Must it possess memories and make decisions? Could an animal qualify? Could an advanced machine? Could a simple detector count as an agent? Or does the interpretation require something capable of genuine probabilistic judgment? Different advocates place the boundary in different ways, and the issue remains unsettled. Multiple agents create another challenge. Two observers may possess different information and assign different quantum states. Later, they meet and compare their experiences. Quantum Bayesianism must explain how their personal accounts become mutually consistent without quietly introducing one objective quantum state beneath them. The agents can update their expectations through communication, but the deeper question remains: what features of the shared external world make agreement possible? There is a clear connection with relational quantum mechanics. Both approaches reject the idea that every system must possess one absolute quantum state, valid from every perspective. Relational quantum mechanics describes physical facts as arising between interacting systems. Any system may serve as an observer in the relevant physical sense. Quantum Bayesianism places greater emphasis on an individual agent's expectations, choices, and experiences. A relational fact concerns how two systems stand with respect to one another. A quantum Bayesian state concerns what one agent expects will follow from particular actions. The difference is subtle, but important. Relational quantum mechanics attempts to describe a world made from physical relations. Quantum Bayesianism treats quantum theory more like a carefully structured guide for agents acting within a world that remains partly independent and partly unpredictable. Its appeal lies in removing several familiar mysteries. Wave function collapse becomes an update of expectations. Non-local state changes become changes in belief. Measurement is an action followed by an experience rather than a vaguely defined physical process that somehow switches the equations. Its difficulty is that many physicists want more from a theory of nature. They want to know what the universe contains when no agent is calculating, choosing, or experiencing anything. Quantum Bayesianism answers that the quantum state was never the thing to ask. It is not the world's private description of itself. It is the agent's best guide to what the world may do next. Eugene Wigner's friend thought experiment places an observer inside the very quantum experiment that another observer is attempting to describe. Imagine a sealed laboratory containing a physicist, a measuring device, and a microscopic system prepared in a superposition of two possible outcomes. The physicist inside the room, usually called Wigner's friend, performs the measurement and sees one definite result. The detector gives one reading. The friend forms one clear memory of what happened. From inside the laboratory, the wave function appears to have collapsed. Eugene Wigner remains outside. If the laboratory is perfectly isolated and every part of it obeys Erwin Schrödinger's equation, Wigner can describe the particle, detector, and friend as one combined quantum system. The measurement interaction does not select one component. It creates an entangled state containing one version of the laboratory in which the first result was recorded and another in which the second result was recorded. The friend says that one event has occurred. Wigner's mathematical description still contains both alternatives. This is not simply a case of Wigner lacking information. If one outcome had already become objectively real, and Wigner merely did not know which one it was, he could describe the laboratory using an ordinary statistical mixture. A coherent quantum superposition is different. Its alternatives retain precise phase relationships that can, at least in principle, produce interference. Wigner could imagine performing an extremely delicate measurement upon the complete laboratory. Rather than opening the door and asking which result the friend observed, he would measure the laboratory in a way designed to reveal interference between the two combined alternatives. If interference were detected, it would suggest that the laboratory had remained coherent in Wigner's description. The friend's measurement would not have produced a universal and irreversible physical collapse, even though it produced one definite experience for the friend. This is where ordinary forgetting differs from quantum entanglement. A person who forgets a result once possessed one definite memory and later lost access to it. In Wigner's scenario, the outside description treats the friend's memory itself as part of the superposition. The uncertainty does not exist merely because Wigner has failed to ask what happened. It is contained in the quantum state he assigns to the entire isolated laboratory. Carrying out such an experiment with a conscious human would be unimaginably difficult. A human observer contains roughly tens of trillions of cells and an even greater number of interacting atoms. Photons, air molecules, thermal radiation, chemical reactions, and electrical activity would rapidly carry information about the result into the environment. Reversing all those interactions would require control of an overwhelming number of microscopic details. Environmental decoherence would make the required interference effectively inaccessible almost immediately. Wigner's friend is therefore not a practical suggestion for placing a slightly concerned physicist inside an unusually complicated box. Its purpose is conceptual. It asks whether a quantum state is absolute. It asks whether facts are observer-independent and whether one event can be definite relative to an observer inside a laboratory while remaining unresolved relative to someone outside it. Daniela Frauchiger and Renato Renner extended this problem by introducing several agents who perform measurements and then use quantum theory to reason about one another's conclusions. Their scenario combines ordinary measurements inside isolated laboratories with outside measurements performed upon those laboratories as complete quantum systems. Each agent uses quantum mechanics to infer what another agent must have observed or must later predict. Under a particular set of assumptions, their deductions become incompatible. The first assumption is that quantum theory can be applied universally, including to laboratories containing observers who are themselves using quantum mechanics. The second is that every measurement produces one single outcome. The third is that agents may combine one another's certain conclusions consistently. If one observer knows that another observer is certain of a result, that certainty should be usable in the wider chain of reasoning. Frauchiger and Renner argued that these commitments cannot all be maintained in their proposed experiment. At least one must be abandoned, restricted, or reinterpreted. Their result did not produce a universally accepted demonstration that quantum mechanics is inconsistent. Physicists continue to debate which assumptions are responsible for the contradiction, whether agents are permitted to combine their state assignments in the proposed way, and how the reasoning changes under different interpretations. Everettian quantum mechanics keeps universal quantum evolution, but rejects the need for one absolute outcome across the complete wave function. Each observer records a definite result relative to a decohered branch, while other results remain in other branches. Pilot wave theory retains one actual configuration of particles. The wave function may contain several components, but the friend, apparatus, and laboratory always possess one definite physical configuration. Objective collapse theories propose that a sufficiently large system undergoes a real physical reduction. Once that collapse occurs, Wigner can no longer correctly describe the laboratory as a coherent superposition of macroscopically different records. Relational quantum mechanics allows the result to be definite relative to the friend, while the laboratory remains superposed relative to Wigner before they interact. Quantum Bayesian approaches treat the two quantum states as expressions of the different expectations held by the friend and Wigner, rather than as competing descriptions of one objective wave function. Modern experiments have constructed simplified versions of extended Wigner's friend scenarios using photons and other carefully controlled quantum systems. In these demonstrations, a small quantum degree of freedom plays the role of an observer by recording information about another system. Researchers can then test inequalities connected with locality, freely chosen measurements, and the assumption that observed events exist as absolute facts for everyone. These experiments do not place conscious human beings into coherent superpositions. They also do not prove that two people literally occupy incompatible realities. Their value lies in translating broad philosophical assumptions into precise statements that experiments can begin to constrain. Wigner's friend forces every interpretation to clarify its language. What qualifies as an observer? When is information merely unknown, and when has no absolute fact been established? At what point does a record become definite? When may one observer adopt another observer's conclusion, as though it belonged to a single shared account? Advances in quantum technology have not caused the measurement problem to disappear. Greater control over entanglement, coherence, and increasingly complicated systems has only sharpened its edges. The more completely an experiment can be included inside the quantum description, the harder it becomes to leave the observer safely outside the mathematics. Wigner's friend is therefore not mainly a story about two physicists disagreeing over a detector. It asks whether reality must provide one description that is simultaneously true from every possible point of view. An experiment can tell physicists whether a prediction is correct. It can reveal whether a particle arrived at one detector or another, whether an interference pattern survived, or whether two distant measurements produced correlations stronger than a classical theory permits. What an experiment cannot always do is decide which description of reality should be placed behind those results. Several interpretations of quantum mechanics are empirically equivalent. This means that they produce the same observable predictions for the experiments currently used to test the theory. A physicist following a Copenhagen approach may describe measurement as producing one definite result. An Everettian physicist may say that every possible outcome remains within a branching wave function. A pilot wave theorist may describe one real particle configuration guided by a non-local wave. A relational interpretation may treat the result as definite only relative to the systems involved. Despite these profound differences, the calculations can lead to the same numbers appearing on the laboratory screen. A perfect agreement between experiment and ordinary quantum mechanics may therefore confirm the shared formalism without selecting one interpretation. If several accounts predict precisely the same observations, no improvement in measurement accuracy can distinguish them through those observations alone. A detector with more decimal places remains an impressive detector, but it does not automatically become a philosopher. This does not mean that all interpretations are scientifically equal in every respect. Physicists also judge theories by explanatory clarity, mathematical simplicity, internal consistency, compatibility with relativity, ability to unify different areas of physics, and precision about what physically exists. An interpretation may be criticized if it depends upon an undefined measurement boundary. Another may require an enormous branching structure. A third may introduce explicit non-locality. A fourth may say little about observer-independent reality. These are genuine scientific and philosophical considerations, even when they do not immediately produce different experimental predictions. Testability remains especially valuable because foundational assumptions can sometimes be translated into measurable restrictions. John Stuart Bell provided the clearest example. Before Bell's theorem, the disagreement over local hidden variables could appear purely philosophical. Perhaps quantum probabilities conceal definite properties carried by particles, with every influence remaining local. Bell showed that such theories must obey statistical limits. Quantum mechanics predicted correlations that could exceed those limits, and repeated experiments supported the quantum predictions. The result did not select one complete interpretation, but removed a broad family of classical possibilities. A related restriction comes from the theorem developed by Simon Kochen and Ernst Specker. Their argument concerns non-contextual hidden variables. A non-contextual model assumes that a measurable quantity possesses one pre-existing value, and that this value does not depend on which other compatible measurements are performed alongside it. Quantum mechanics does not generally permit such a simple assignment. The Kochen and Specker theorem shows that it is impossible to give every quantum observable a predetermined value while preserving the relationships required by the theory and keeping those values independent of measurement context. This introduces contextuality. A quantum result cannot always be understood as the revelation of one item from a complete classical list already carried by the system. The outcome may depend upon the wider measurement arrangement in which the observable appears. Contextuality does not mean that laboratory results are arbitrary or created by personal opinion. The probabilities remain precisely constrained by quantum mechanics. It means that properties cannot generally be separated from the physical context used to measure them. Matthew Pusey, Jonathan Barrett, and Terry Rudolph placed another restriction on possible interpretations. Their theorem examines models in which the wave function represents incomplete information about a deeper physical state. Under assumptions, including preparation independence, distinct quantum states cannot merely correspond to overlapping uncertainty about the same underlying reality, while still reproducing all quantum predictions. The result places pressure on simple attempts to treat the wave function like an ordinary probability distribution over hidden classical states. It does not prove that every epistemic interpretation is impossible. The conclusion depends upon the assumptions used in the argument. A proposed model may reject preparation independence or change the nature of the underlying physical state. These theorems show how interpretation can become experimentally and mathematically constrained without becoming completely settled. Objective collapse theories offer one of the clearest opportunities for a more direct experimental decision. Unlike interpretations that preserve standard quantum predictions, collapse models alter the dynamics. They propose that sufficiently large superpositions physically reduce to one outcome through a spontaneous process. This may produce tiny losses of interference, unexplained heating, spontaneous radiation, or other departures from ordinary quantum mechanics. Matter wave interferometers test increasingly massive molecules and particles. Optomechanical experiments attempt to control the quantum motion of small mirrors, membranes, and suspended objects. Cold atoms, underground radiation detectors, and precision measurements place limits on possible collapse rates and localization scales. No confirmed departure from standard quantum mechanics has yet established objective collapse. Experiments can exclude particular parameter ranges without ruling out every possible collapse theory. The boundary between ordinary quantum behavior and genuine physical reduction may be weaker, rarer, or structured differently from the versions already tested. Quantum gravity may eventually change the debate more dramatically. Ordinary quantum mechanics is usually applied within a fixed background of space and time. General relativity describes space-time itself as dynamical, shaped by matter and energy. Combining these theories may force physicists to reconsider the meaning of the quantum state, time, measurement, locality, and observation. Quantum cosmology creates a related difficulty. The universe as a whole has no external apparatus waiting outside it. Any interpretation that relies upon a special observer or classical measuring system must explain how its rules apply when every observer and instrument is contained inside the quantum universe. Each major interpretation faces challenges at this deeper level. Pilot wave theory must accommodate relativistic quantum fields, particle creation, and dynamical spacetime while preserving a coherent account of non-local guidance. Objective collapse theories require relativistic collapse mechanisms that do not produce contradictions with causality or unacceptable energy effects. Everettian quantum mechanics must explain branching, probability, and familiar three-dimensional reality within quantum fields and cosmology. Relational and information-centered approaches must clarify whose facts, relations, or expectations remain meaningful when spacetime itself becomes quantum. Disagreement also persists for practical reasons. Most working physicists can calculate experimental results without choosing a detailed interpretation. Quantum mechanics already performs its daily duties extremely well, and research careers are often built around measurable particles and devices rather than debates over what the wave function privately considers itself to be. Different physicists also demand different things from an explanation. Some value a clear ontology describing what exists. Others prefer minimal mathematics without additional invisible structures. Some accept non-locality more readily than branching universes. Others consider the demand for an observer-independent picture unnecessary. There is no formal vote capable of deciding which view is true. A survey may reveal what physicists currently prefer, but popularity cannot determine the structure of reality. Scientific judgment must rest upon consistency, explanatory power, connections with other theories, and any new experimental differences that can be uncovered. Existing evidence has already taught us something important. Nature cannot be described by every imaginable classical model. Local hidden variable theories face Bell's restrictions. Non-contextual assignments face the Cauchy and Specker theorem. Simple informational accounts of the wave function are constrained by the assumptions examined by Matthew Pusey, Jonathan Barrett, and Terry Rudolph. Yet no experiment has established Copenhagen quantum mechanics, Everettian quantum mechanics, pilot wave theory, objective collapse, relational quantum mechanics, quantum Bayesianism, or consistent histories as the uniquely correct account. One of these approaches may be substantially right. A future experiment may reveal a small failure of standard quantum dynamics and point towards real collapse. Quantum gravity may favour a relational or histories-based framework. A deeper theory may explain the apparent strengths of several interpretations while showing that none is fundamental. It is also possible that physicists are still trying to describe quantum reality using conceptual categories that will eventually appear as limited as the classical assumptions that came before them. Experiments can narrow the possibilities, they can remove comforting answers that nature refuses to support. What they have not yet done is force the surviving interpretations into one final picture of what the universe is. Physicists still cannot agree on what quantum physics means, but the disagreement begins from an extraordinary point of unity. They share a mathematical framework that predicts the behavior of atoms, particles, light, and matter with remarkable accuracy. They agree on how to calculate interference patterns, energy levels, entangled correlations, and the probabilities of measurement outcomes. The uncertainty begins when they ask what the wave function, those probabilities, and the act of measurement represent in physical reality. Classical physics encouraged the expectation that objects possess definite properties at every moment. A particle should have one position, one motion, and one history, whether or not anyone observes it. Quantum mechanics replaced that familiar picture with superposition, uncertainty, entanglement, and a wave function containing several possible outcomes. Measurement then appeared to produce one definite result. Although the smooth quantum equations did not clearly explain why only one possibility should remain, different interpretations preserve different parts of the old expectation. The Copenhagen family stays close to laboratory practice. It treats classically described outcomes as essential, while remaining cautious about claims concerning an unobserved microscopic reality. Its practical strength is considerable, but the precise meaning of measurement and wave function, collapse, remains difficult to define. Everettian quantum mechanics removes collapse entirely. The universal wave function evolves without interruption, and every outcome continues within a decohered branch. One simple quantum law applies everywhere, although reality becomes populated by an enormous multiplicity of branch relative experiences. Pilot wave theory restores definite particle positions and continuous trajectories. One actual configuration exists, guided by a wave function connecting the complete system. Its clarity comes at the price of a fundamentally non-local structure. Objective collapse theories take another route. They modify quantum dynamics so that superpositions genuinely reduce to one result. Collapse becomes random, physical, and independent of observation. Unlike many interpretations, these models can produce small deviations from standard quantum predictions, and may therefore be tested by increasingly sensitive experiments. Consistent history shifts attention from isolated measurements to whole sequences of quantum alternatives. Relational quantum mechanics treats properties as facts established between interacting systems, rather than as absolute possessions. Quantum Bayesianism interprets the wave function as an agent's organized expectations about future experiences. Each approach changes what is meant by states, facts, probability, or observation. Decoherence provides an important piece shared across much of the debate. Environmental interactions explain why macroscopic alternatives rapidly lose their ability to interfere. They help produce stable pointer readings, durable records, and the approximately classical world of everyday experience. Yet decoherence does not decide whether the alternatives truly collapse, continue as branches, guide one particle configuration, or become definite only relative to particular systems. John Stuart Bell demonstrated that foundational questions need not remain entirely philosophical. Bell's theorem translated assumptions about locality and hidden variables into measurable statistical restrictions. Experiments then ruled out broad classes of local classical explanations. Even so, the surviving interpretations were not reduced to one. This does not mean that quantum mechanics is defective. A theory can produce precise and reliable predictions before its deepest conceptual meaning is fully settled. Science has often learned how nature behaves before reaching agreement about why its successful descriptions take the form they do. Predictive success, however, does not make the foundational questions unimportant. Quantum mechanics must eventually fit into a deeper understanding of gravity, space-time, cosmology, and the universe as a closed physical system. In those settings, there may be no external observer, classical apparatus, or laboratory boundary available to hide unresolved assumptions about measurement. The disagreement is not evidence that physicists understand nothing. It reveals something more subtle. The same successful mathematics permits radically different accounts of what exists. Reality may contain genuine collapses, branching worlds, guided particles, relational facts, personal probabilities, or a deeper structure that no current interpretation has described completely. Quantum physics tells us with extraordinary precision what observations will reveal. What the universe is doing before, during, and beyond those observations remains one of the quietest and deepest unanswered questions in science.